Have you ever noticed how a slice of apple turns brown after being left out for some time? Or how a candle, once lit, turns to smoke and wax strips? These everyday occurrences are chemical changes at work. A chemical change is a permanent transformation, one where new substances form and are usually quite different from what we started with. What makes it truly fascinating is you can't easily undo it. Once paper burns, you can't get it back. That's because, at a molecular level, the structure has changed completely. How do we know a chemical change has occurred? We look for signs. A new color appears, a gas might evolve, heat or light is given out, or sometimes a solid precipitate forms. For example, when magnesium ribbon burns in air, we see a dazzling white flame and white ash, a sure sign of a chemical change. As you'll see on screen, this is a clear before and after picture of magnesium combustion. Let's now understand what really happens in a chemical change. We call that a chemical reaction. A chemical reaction is the actual process where one or more substances, called reactants, interact and transform into new substances, called products. And in chemistry, we love to express things clearly. So we use chemical equations. For example, hydrogen gas plus chlorine gas gives hydrogen chloride, written as H2 gas plus Cl2 gas forms to HCl gas. This simple equation hides the magic of bond breaking and bond forming. And guess what? The food we eat, the rust on iron, and even life on Earth all involve chemical reactions. One classic example is photosynthesis, the process where green plants convert carbon dioxide and water into glucose and oxygen using sunlight. As you can see on the screen now, this reaction supports life itself, one of the most beautiful examples of chemistry in nature. How do we confirm that a chemical reaction has really taken place? Well, your eyes, ears, and nose can often tell. Color changes are a big clue. Take the example of iron dipped into copper sulfate solution. The blue color fades and reddish copper coats the iron nail. Or think of fizzing reactions like zinc reacting with dilute hydrochloric acid. You'll hear a sizzle and see bubbles. The equation is zinc solid plus 2 HCl aqueous gives ZnCl2 aqueous plus H2 gas. In some reactions, a solid forms from two solutions, that's called a precipitate. For example, barium chloride reacting with sodium sulfate forms a white precipitate of barium sulfate. And don't forget the energy, many reactions either release or absorb heat. Just like how fire warms your hands, a clear sign of an exothermic reaction. You'll now see on screen an experiment showing gas bubbles released when zinc reacts with acid, quite the chemistry show. Let's talk about what defines a chemical reaction at its core. First, a new substance is always formed and it's chemically different from the starting materials. Second, the law of conservation of mass always holds true. That means the mass of reactants equals the mass of products, no matter what. Third, there's usually an energy change. In exothermic reactions, energy is given out like combustion. In endothermic ones, it's absorbed like photosynthesis. And fourth, most chemical reactions are irreversible. Once it happens, it's tough to go back. Here's a familiar example. When an acid reacts with a base, heat is produced. That's a classic neutralization reaction, and you'll definitely feel the warmth if you touch the beaker. All chemical reactions don't look the same, they behave differently. So chemists classify them into types. First, we have combination reactions, two substances joined to form one. For example, calcium oxide plus water gives calcium hydroxide, or CaO plus H2O gives CaOH2. Second, decomposition reactions, A single compound breaks into simpler substances. 2Hgo on heating gives 2Hg plus O2. Third, displacement reactions, where a more reactive element kicks out a less reactive one. Zinc plus copper sulfate gives zinc sulfate plus copper. Fourth, double displacement reactions, two compounds exchange ions. Sodium sulfate plus barium chloride gives barium sulfate precipitate plus sodium chloride. On the slide, you'll see a flowchart that maps out these types with clear examples like a reaction family tree. Now let's bring this to the lab. Imagine placing a clean iron nail into a beaker containing bright blue copper sulfate solution. Leave it for 20 minutes. What happens? A reddish brown coating forms on the nail and the solution turns pale green. Why? Because iron is more reactive than copper. It displaces copper from the solution. The reaction is Fe plus CuSO4 gives FeSO4 plus Cu. So, iron becomes iron sulfate and copper gets deposited, a classic displacement reaction. As the experiment set up on screen shows, this simple test reveals so much about the reactivity of metals and chemical change in action. Let's quickly revise what we've explored about chemical changes and reactions. We saw that chemical changes are permanent, involve new substances, and show visible clues like color shifts, gas bubbles, or energy changes. We defined chemical reactions as the actual process where substances, called reactants, are transformed into new ones, the products. We walked through examples, equations, and real world analogies, from burning candles to photosynthesis in plants. You even got a peek into lab reactions like iron displacing copper, a simple experiment with deep chemistry behind it. I hope this session helped you understand that chemical reactions aren't just in books, they are everywhere, shaping our world. From the food we eat to the air we breathe, it's all chemistry in motion. See you in the next class, where we'll explore the fascinating world of types of chemical reactions and how they drive life and industry.